The periodic table in environmental chemistry. What do nitrogen pollution, toxic heavy metals, and soil nutrients all have in common? They're all elements on the periodic table, and understanding where they sit on this chart can help us predict environmental disasters before they happen. The periodic table isn't just a chemistry classroom poster. It's a powerful predictive tool that environmental scientists use every day to understand pollution, protect water quality, and manage ecosystems. The periodic table, your essential guide to environmental chemistry. What is the periodic table? The periodic table is a scientific chart that organizes all known chemical elements in a logical, systematic way. It arranges elements based on three key factors: their atomic number, which is the number of protons in the nucleus, their electron configuration, and their recurring chemical properties. This structure isn't random. It allows scientists to predict how elements behave in chemical reactions and how they interact with the environment. In environmental chemistry, the periodic table is absolutely essential. Different elements play crucial roles in nutrient cycling, pollution formation, soil chemistry, water quality, and atmospheric reactions. Understanding the periodic table means understanding the building blocks of our environment. Structure. Periods. The periodic table is organized into 7 horizontal rows, called periods. Each period represents elements with increasing atomic number as you move from left to right. What makes a period special is that all elements in the same period have the same number of electron shells, though they differ in chemical properties. Take period 2, for example. It contains lithium, carbon, nitrogen, and oxygen, all elements that are vital to environmental processes. Nitrogen drives the nitrogen cycle. Oxygen is essential for aerobic respiration and oxidation reactions. Carbon forms the basis of organic chemistry and climate-regulating carbon dioxide. The period tells us about an element's atomic structure, which influences how it behaves in nature. Structure. Groups. The vertical columns are called groups or families. This is where the periodic table's predictive power really shines. Elements in the same group have similar chemical properties because they have the same number of valence electrons, the electrons in the outermost shell that participate in bonding. Group 1 contains the alkali metals like sodium and potassium. These are highly reactive metals that readily lose one electron. They're essential nutrients in ecosystems but can also alter water chemistry. Group 17 contains the halogens: fluorine, chlorine, bromine, and iodine. These are reactive non-metals that gain one electron. Chlorine is used in water disinfection, but chlorofluorocarbons have damaged the ozone layer. Understanding groups helps explain why certain elements form pollutants, act as nutrients, or become toxic compounds in the environment. Blocks of the periodic table. The periodic table is also divided into blocks based on electron configuration. The S block contains alkali metals and alkaline earth metals, reactive elements that form important ions in water and soil. The P block includes nonmetals, halogens, and noble gases. This block contains elements essential for life: carbon, nitrogen, oxygen, phosphorus, and sulfur. The D block contains transition metals like iron, copper, zinc, and mercury. These metals participate in critical environmental reactions, but can also become serious pollutants. The F block includes lanthanides and actinides, many of which are radioactive and pose environmental hazards. These blocks help chemists understand patterns in reactivity, ion formation, and bonding, all key factors in environmental processes. Types of elements. Metals. Metals make up the majority of elements in the periodic table. They're typically shiny, good conductors of heat and electricity, and can easily lose electrons to form positive ions called cations. In environmental chemistry, metals are extremely significant. Iron is essential for plant growth and participates in redox reactions in soil and water. Copper and zinc are micronutrients, but become toxic at high concentrations. Mercury, lead, and cadmium are toxic heavy metals that bioaccumulate in food chains, poisoning wildlife and humans. Understanding metal chemistry helps us predict pollution behavior and design remediation strategies. Types of elements. Non-metals. Non-metals have diverse properties, but are generally poor conductors of heat and electricity. They tend to gain electrons to form negative ions called anions. Key environmental elements are non-metals. Oxygen drives oxidation reactions and supports aerobic life. Nitrogen is the most abundant atmospheric gas and a limiting nutrient in ecosystems. Sulfur forms acid rain when oxidized in the atmosphere. Phosphorus is essential for plant growth, but causes eutrophication when present in excess. These elements are involved in major biogeochemical cycles that sustain life on Earth. Types of elements. Metalloids. Metalloids have properties between metals and non-metals, giving them unique environmental significance. Silicon is the second most abundant element in Earth's crust and forms the backbone of soil minerals and clays. Arsenic is a toxic metalloid that contaminates groundwater in many regions worldwide, particularly in Bangladesh and parts of Southeast Asia. Understanding arsenic chemistry helps environmental scientists develop water treatment solutions and assess health risks. Periodic trends. Atomic radius. The periodic table reveals predictable trends that explain element behavior. Atomic radius is the size of an atom. It increases as you move down a group because each period adds an electron shell. It decreases as you move across a period from left to right because the nucleus contains more protons, pulling electrons closer. This trend affects how elements bond, how ions move through soil and water, and how pollutants interact with environmental particles. Periodic trends. Electronegativity. Electronegativity is the ability of an atom to attract electrons in a chemical bond. It increases across a period from left to right and decreases down a group. Oxygen, nitrogen, and fluorine are highly electronegative elements. This property explains why they form strong bonds and participate in critical environmental reactions. Oxygen's high electronegativity drives acid formation when combined with sulfur or nitrogen oxides. Nitrogen's electronegativity influences nutrient availability in soils. Understanding electronegativity helps predict which compounds will form and how stable they'll be in the environment. Periodic trends. Ionization energy. Ionization energy is the energy needed to remove an electron from an atom. It increases across a period and decreases down a group. Elements with low ionization energy, like sodium and potassium, lose electrons easily and react readily. This explains why these alkali metals are so important in soil chemistry. They're easily released from minerals and absorbed by plants. Elements with high ionization energy, like noble gases, rarely react at all, which is why they're called inert gases. Periodic trends. Reactivity. Reactivity varies depending on whether an element is a metal or non-metal. For metals, reactivity increases as you move down a group. Potassium is more reactive than sodium, and cesium is extremely reactive. For non-metals, reactivity increases across a period and up a group. Fluorine is the most reactive non-metal, followed by oxygen and chlorine. Understanding reactivity helps explain why some elements form environmental pollutants more readily than others, why certain metals corrode quickly, and how chemical weathering proceeds in soils. Environmental applications. Nutrients. The periodic table helps identify essential nutrients and explain their environmental roles. Nitrogen and phosphorus are macronutrients critical for plant growth, but excess amounts cause eutrophication, algal blooms that deplete oxygen and kill aquatic life. Potassium, calcium, and magnesium are essential for soil fertility and plant health. Micronutrients like iron, zinc, copper, and molybdenum are needed in trace amounts, but are equally vital for ecosystem function. By knowing an element's position on the periodic table, we can predict whether it will be a limiting nutrient or a pollutant. Environmental applications. Toxic metals. Heavy metals like lead, mercury, and cadmium occupy specific positions on the periodic table that explain their toxic behavior. These transition metals can displace essential metals in biological enzymes, disrupting metabolism. Mercury bioaccumulates in fish, becoming more concentrated up the food chain. Lead damages nervous systems, especially in children. Cadmium causes kidney damage and bone disorders. The periodic table helps environmental scientists predict which metals pose the greatest risks and design monitoring programs accordingly. Environmental applications. Atmospheric chemistry. Halogens in Group 17 play crucial roles in atmospheric processes. Chlorine and bromine from human-made chlorofluorocarbons and halons catalyze ozone destruction in the stratosphere. Oxygen and nitrogen, both non-metals, dominate atmospheric chemistry. Nitrogen oxides contribute to smog and acid rain. Oxygen drives combustion and oxidation reactions. Understanding these elements' positions and properties helps explain atmospheric pollution and climate chemistry. Environmental applications, redox reactions, transition metals in the D block participate in important oxidation reduction reactions in aquatic systems. Iron exists in two forms: ferrous iron, Fe2+, and ferric iron, Fe3+, depending on oxygen availability. These redox reactions control metal mobility, nutrient availability, and pollutant transformation. Manganese, copper, and other transition metals undergo similar transformations that influence water quality and ecosystem health. The periodic table's organization helps predict which elements will participate in redox chemistry. Why the periodic table matters. The periodic table is more than a reference chart. It's a predictive tool that allows environmental scientists to anticipate chemical behavior before problems occur. It helps determine which elements are likely to form toxic compounds, which are essential nutrients, and how pollutants might move through air, water, and soil. It reveals patterns in reactivity, bonding, and transformation that govern every environmental process. From predicting soil fertility to understanding atmospheric ozone depletion, from managing heavy metal contamination to preventing eutrophication, the periodic table provides the fundamental framework for environmental problem solving. Summary: this lesson has provided a foundational understanding of how the periodic table is organized and why it's essential in environmental chemistry. The arrangement of elements into groups, periods, and blocks helps predict their chemical behavior. Periodic trends, atomic radius, electronegativity, ionization energy, and reactivity explain why elements behave differently in natural systems. Metals, nonmetals, and metalloids each play distinct environmental roles. This knowledge is crucial for studying environmental processes and addressing chemical-related environmental issues throughout your studies and career. Closing message: master the periodic table, and you master the language of environmental chemistry. Every element has a story, a role, and a potential impact on our planet. The periodic table, your key to understanding environmental chemistry. Subscribe for more environmental science lessons.